The discussion of the fundamentality of space in physics raises doubts about whether it is the fundamental element or simply a product of our brain's perception. Einstein's theory of general relativity conflicts with quantum mechanics, leading to alternative theories such as string theory and loop quantum gravity. However, testing these theories has proven challenging. Nonetheless, combining general relativity and quantum mechanics suggests that spacetime exhibits a foamy nature at the smallest scales, similar to waves and foam on the surface of the ocean. And if you're in a rowboat, the wave would be everything. You'd be moving through a space that was far from flat, but rather dominated by ever-changing geometries. In this analogy, the 2D surface of the ocean is three-dimensional space. For large creatures like us humans, we're flying high above and see smooth, flat, and perfectly continuous spatial dimensions. But descending closer to the Planck scale, we would see ubiquitous tiny fluctuations as distances and geometries became warped. And at the Planck scale, spacetime would become so curved that black holes and wormholes would be popping into existence, only to vanish again, as if our ocean were now violently boiling. This is Wheeler's spacetime foam, and there's good reason to think that spacetime really does look like this when you're close to the smallest scales, regardless of your preferred theory of quantum gravity. We need the latter to say what spacetime is made of, to understand the analogous level of the water molecules in our ocean. However, the behavior of a quantum spacetime just above that level can perhaps be understood regardless of its underlying theory, just as we can describe the behavior of water without knowing its chemistry. Today we're going to see where the idea of spacetime foam came from and also how it might be tested. Now we'll do this by combining two of the fundamental ideas in each theory of the fundamental theories, the uncertainty of quantum mechanics and the geometry of general relativity. Because spacetime foam is what you get when geometry itself becomes uncertain. Let's start with a bit about uncertainty. The Heisenberg uncertainty principle is one of the foundational concepts in quantum mechanics. The Heisenberg uncertainty principle states that we cannot simultaneously know the position and momentum of a particle with arbitrary precision. The product of their uncertainties will always be larger than a very small number. One way to understand this principle is through the Heisenberg microscope thought experiment. When trying to measure the position of an object by bouncing a photon off it, a more precise position measurement can be obtained with a shorter wavelength photon. However, this photon transfers momentum to the object, causing uncertainty in its final momentum. There is a limit to the precision of position measurement due to the introduction of uncertainty in the geometry of space by mass and energy, as described by general relativity. As the measuring photon gains momentum and energy, it increases uncertainty in the distance to the object. When the uncertainty in position and the uncertainty in the geometry of space are equal, which occurs at the Planck length of 1.6 x 10⁻⁻35 meters, it becomes the absolute limit of our ability to pinpoint objects in space. To measure the size of a small block of space, the wavelength of the measuring photon must be smaller than the width of that block. The introduced curvature from the photon can be comparable to the size of the space being measured. When trying to measure the size of a 1 Planck length block of space, the introduced curvature is equal to a Planck length. This combination of quantum mechanics and general relativity gives us a glimpse into the concept of spacetime foam. As we examine the fabric of spacetime more closely, its curvature becomes increasingly variable and uncertain, eventually dominating the overall geometry. This implies that at the Planck scale, geometries such as spheres, cylinders, and black holes emerge. Space at this scale exhibits complete self-curvature, featuring infinitesimal black holes and interconnected wormholes. However, these Planck-scale black holes would likely evaporate quickly due to Hawking radiation, and the wormholes would be unstable and prone to collapse. To comprehend the dynamics of spacetime foam, we can consider quantum fluctuations. The Heisenberg uncertainty principle tells us that we cannot simultaneously know the energy and duration of an event. Therefore, if we attempt to precisely measure a system's energy at a specific time or over a short duration, the energy measurement becomes highly uncertain. This implies that there is a fundamental uncertainty in the physical contents of the universe. In quantum field theory, which describes matter and three of the four fundamental forces as excitations in quantum fields pervading space, the energy of a particular space region can never be precisely known. Even in the absence of real particles, there may be a non-zero energy that becomes more likely with shorter observation timescales. This gives rise to a buzzing background of rapid energy fluctuations in the quantum vacuum, often described as an ocean of virtual particles appearing and vanishing, although the reality is more complex. The uncertainty in the shape of spacetime fabric can be attributed to the fluctuating energy of the vacuum, which introduces uncertainty in the mass-energy content and therefore the corresponding geometry of space. Virtual particles appearing and disappearing momentarily result in transient gravitational fields, contributing to the complex and ever-changing nature of spacetime at the Planck scale. These quantum fluctuations can give rise to exotic phenomena such as wormholes, and the superposition of many different states implies that multiple geometries coexist simultaneously. The macroscopic scale observation appears flat due to the combined effect of all Planck scale configurations. The foamy nature of spacetime arises from the intrinsic uncertainty in the contents of space, or the geometry of spacetime itself. This conclusion arises from the application of the uncertainty principle to gravity, suggesting that spacetime should be foamy at the Planck scale. Direct tests of this concept are challenging due to the minuscule scale involved, which is beyond our current technological capabilities. However, indirect tests are possible. As John Archibald Wheeler's analogy of spacetime foam as a choppy ocean surface suggests, we can explore this concept further. A gigantic ship doesn't notice waves, while a rowboat does. A vessel in between may have a smoother ride, but still experience slight deviations over time on a wavy ocean compared to a calm one. If spacetime foam exists, particles traveling long distances may undergo slight changes in their trajectory. This can be tested with a simple experiment involving diffraction patterns produced by a distant point of light. Photons that arrive at different angles will generate different interference patterns, resulting in a blurry image. Several studies have attempted to detect the impact of spacetime foam on diffraction patterns in data from the Hubble Space Telescope. Although certain models have been ruled out, measurements are approaching the required sensitivity, suggesting the possibility of detecting this effect with a larger, more sensitive space telescope.